It says calculate the rotational kinetic energy of, oh, I know why I did this one. I had a very specific point I want you to bring up. So, and let's try to save a little bit of time on this question. So it's asking about rotational kinetic energy. And I don't think that part is that hard, at least the formula for it. The rotational kinetic energy is going to be, it's an analogous version of, sorry, I meant to say kinetic energy. So kinetic energy, rotational, is going to be equal to, it's going to be an analogous version of the translational kinetic energy, which was 1/2 mv squared. So the analogous version here is 1/2 times the I, rotational inertia, times V, not V, times omega squared. So in terms of formula, it's not that hard. It even tells you what the angular velocity is. So, so it looks like all you need to find is I, and that is why I'm here to try to give you a sense to how to figure this out. I guess the geometry of a wheel that it's describing, it might be common enough that you can actually find a formula for it. If you can, great, I guess you can use it. Let me assume that you haven't found the formula. So let me kind of draw what the geometry of this wheel looks like. So it's a wheel, everyone here knows what wheels look like. The question is giving you the inner radius and the outer radius. So let me draw a perspective view that kind of illustrates that. So what I'm going to draw is basically a donut, or something that kind of is donut shaped. So I'm exaggerating a little bit, of course. So something of this shape is what you are asked to deal with. And here's the interesting thing. So this particular geometry may not be in the list of geometries that you have for your table of rotation inertia. So if that's the case, how do you do? So this is where an idea called the superposition principle can be very useful. It's this idea. So you have, this donut-shaped object, and the idea of superposition principle is this. It's the idea that this donut shape, let me do it this way. This donut shape can be decomposed into these two parts. So let me make a copy of that. Oops. So donut shape as a whole, I have no idea how to, well, I do have some idea, but the idea I have for how to calculate its rotation inertia is super complicated. It takes very long. So this is what I want to do. I want to describe the donut shape as being made out of two parts. And these are the two parts. You have a disk, a solid disk of rotational, a solid disk of the outer radius. All right. And imagine this inner radius not making up a whole, but instead making up another disk of the same size and density as the material for the larger disk. So we are talking about the same density of material. Then you can describe this object A as being made up of object B minus object C. This is what we mean superposition principle, that you have some property, rotational inertia, that corresponds to some complex object. And in general, it wouldn't be true that you can take the complex object into bits and pieces, work it out for all those bits and pieces and put them back together. In general, that doesn't always work. Imagine taking a human being, taking out each little bit, and then, sorry, a little bit too gruesome. But in physics, it turns out to work in a lot of situations. So for situations where that works, we say that superposition principle applies in this case. And you're going to see one more example of superposition principle in this class, but this is one of them. So it's worth mentioning it now. So we say that rotational inertia of this object A can be described as, in this case, rotational object of the disk B, and this time I'm subtracting the rotational inertia of disk C. So once you get to this point, then it becomes pretty simple to describe the rotational inertia. Rotational inertia of a disk is equal to 1/2 mass of the disk times the radius of the disk squared. So using the superposition principle here, what we can say about rotational inertia of A, I guess I'll leave that as symbol, is going to be rotational inertia of B, which is 1/2 mass of B times the radius of B. So this is what I would call radius of B squared minus 1/2 mass of C times the radius of the disk C. This is what I'm going to see, what I'm going to call radius of C. So radius of C squared. So when you look at this expression, you don't quite have all the information because the question gives you the mass of the entire wheel, but let me call this M, but you have it in terms of MB and MC. So you kind of need to have a couple more expressions that relate those quantities. I think I can say these things. Hopefully, as I say them, it makes sense. The big mass M there, that's the mass of B minus mass of C. Hopefully that makes sense. You can relate how the mass of B and mass of C compare. So imagine taking the ratio of M sub B to M sub C. Then I hope you have some intuitive sense that these masses are going to be proportional to this base area. You imagine them as having the same thickness. So whichever has more, if something has twice the base area, then it has twice the mass. Hopefully that makes sense. So now in terms of this radius, then the base area is going to scale this way. The base area of B to base area of C should equal the radius B squared over radius C squared. So that makes sense. And this ratio of the areas is the mass of the area, MB over MC. So, all right, so then it's the RB squared over RC squared. And I think that's enough. Here I have three unknowns, MB, MC, and M, and I have three equations. Is that right? Yeah, I have three equations. So I can, for example, solve this equation for MB and plug that into both the expressions here and here to get rid of MB. Then from expression here, I can solve it for MC. and plug that into this expression twice to get an expression in terms of M alone. Oh, I know what was confusing me. M is not the unknown. The rotational inertia is the unknown. So, but from here on, it's a simple algebra to get to the rotational inertia. And once you have rotational inertia, then the rest of the question isn't too hard. So let me leave you there in the interest of time. So, but I want you to talk about, briefly talk about this superposition principle. That's why I had this in the list.